Hi everyone, thanks for joining in. I'm Yuri van Leeuwen from Astron and University of Amsterdam. And in the next 10 minutes I want to give you a quick use case of our radio pulsar search on the grid. So radio pulsars are stars that are formed in big explosions. Here's one, real image. And in the center of that is now an extremely compact object, like a lighthouse. It emits bursts, and bursts like these, in this case, travel 5,000 years before they hit the radio telescope. LOFAR. LOFAR is a revolutionary new radio telescope that we've just built in the Netherlands and actually throughout Europe. So what are pulsars like? Pulsars are formed when stars explode, and then in this explosion these central cores, these are 1 million times more massive than the Earth, more massive than our Sun even, they get to spin very rapidly. If you then take the radio emission that these radio telescopes pick up and you change that to audio, like your radio does, it's something like this. So about once a second this pulsar spins. This is only a sphere 10 times the size, 10 kilometers across, so the size of Amsterdam, but 1 million times more massive than the Earth. So if you think that's impressive, and I think it is, you should listen to one of those new ones, the ones that are just born in these big explosions. They sound like this. So if you think about that mass and spin, that's a huge amount of rotational energy right there. That makes these pulsars extremely stable clocks. I'll talk about that in the next slide. The most exciting ones, though, are the ones that are born in double star systems, as you'll see in a bit. Those spin even faster, so fast that you can't even hear the individual ticks anymore, and neither can you see the individual beams. So that's 700 times a second a pulsar spins. So how are these formed? They're formed in binary stars. About half of the stars in our universe live in binary stars, so like sister systems. First the big ones explode, the most massive ones go first. They form a black hole or a neutron star. I'm talking about neutron stars right now, or pulsars. And they emit beams of radiation, like you can see here. Then if there's a second sister star system that grows, then this massive pull of the pulsar tears off the outsides of that star, makes it spin faster, and then you get two. There's a bunch like these known, a slow one and a fast one. One is just born and the other one got spun up. Now why are we excited about that, beyond the fact, for example, that this is the highest gravity pull you can see anywhere in the universe? We're excited because this extreme energy means that these stars are also very stable rotators, and that means you can use them as very good clocks. So let me show you what that works like here. Just a sec while I get this going. There we go. So we have two massive star systems, and in the center of each lives a great 1 million solar mass black hole. The center of our Milky Way has one too. That's really close, actually. But for these massive star systems to grow, these Milky Ways to grow, these black holes at the center, they need to merge. And at the end, this means they emit a lot of gravitational wave energy. And you can see the gravitational waves depicted here with this green mesh. Gravitational waves are a prediction by general relativity, and if we want to test what our understanding of general relativity is like, we need to test if these gravitational waves exist. They travel throughout the universe, they permeate basically everything, and they also pass Earth all the time. And they move Earth around. Every time a wave like this passes Earth, the Earth moves by a few meters. We don't feel this because we're on it. But you could measure this by looking at a distant clock, a very stable one, a radio pulsar for example, and then seeing the Doppler shift of the pulsar clock signal. You can depict it here in red and blue. So if you have a bunch of these fast spinning pulsars all over the globe, you have basically a universe time frame. So that's what we're aiming to do. Sorry, let me go to the next slide. There we go. So that's what we're aiming to do. We're trying to find new pulsars in radio telescope data. And that is also the problem that we're trying to solve. Because radio telescopes are extremely data intensive. For a survey like this, so the search that we're trying to do for new sources, each data set is about 20 gigabytes. That's just one data set. And there's thousands of data sets like that. I'll talk about the total data volume in a bit. The things we need to do are basically first getting these two-dimensional data arrays collapsed in about 10,000 different ways. So we need to do a shift add. That's a highly I/O and compute-intensive job. Next, the resulting 1D vectors need all to be Fourier transformed, because in that Fourier space you can actually see the pulsar periodicity. And we need to do some match filtering for various different other pulse shapes. And overall, this amounts for each hour of telescope time on a modern machine to about 1,000 core hours. So that's a significant amount, because just our first pilot survey, which was just 1% of the sky, is already 1,000 telescope hours, and that's 1,000,000 core hours. And that's just a okay. So in that sense, this whole system is very much like your visual system. LOFAR, the telescope, is the eyes. We have 19. Actually, this telescope can look at 19 directions at the same time. You need an optical nerve to go from the visual center to the compute center. So from your eye to your brain. In our case, that is a 10 gigabit per second light path between LOFAR and the grid storage center here at Amsterdam. And finally, you need, of course, the memory and the compute. And that's what the grid jobs were for. Memory was the tape storage in Amsterdam, and the compute were the grid clusters. So how did we actually get about to implement this? The software that we're trying to use has been well tested and proven, and I don't really want to change it much, but it is eclectic. Some parts are written in the early 70s, so Fortran, that's hard to read. But I don't want to change it, because 2 Nobel Prizes were won with that very software, so I'm not touching that. But it means that it's sometimes a little complicated to install, especially when, like on the grid, between different sites there are small variations. So in our case, and I think this is important, just start by choosing one site and get your code to work there. That's the way we started, and then from then on you can make smaller iterations while you move out and move to different processing sites. Something that was specifically a problem for us, for example, that our software expects to be run from a path that it knows beforehand. So once you install it somewhere, it expects to always be called from that. It's just old school. Which is not that easy on the grid, because often you send a tarball of your software to some place and you don't know where it's unpacked. It's probably in some temp directory somewhere. So in our case, what we did was basically always make a link to some predefined path that we could always expect to exist or be made. So in this case, that's just something in /temp with our overall job name. For me, the most important lesson was, though, and this was the first time I did major computing on the grid, talk to someone at your local NGI and get their support and advice. And it was really through that team interaction, for me it was very much a team interaction, that we were able to set this up and move to a much bigger scale of grid computing than I previously thought was possible and doable. So I'm very happy with that. So the way we got it set up was basically that we had every time in the queue about 1,000 pilot jobs. Every time a pilot job hit when it got executed, it would actually pull a token server, in our case Topos, and ask it, okay, what next? And this for us made it much easier to always keep our slots filled, and also to have a good feel on what gets processed and what needs to be reprocessed in case of failed jobs. So the jobs, they just pick up basically a 4-line token that all it does is says, okay, this is the data file you now need to go find, here's the location you can grab it from. Any results, please upload them back to the grid storage at this and this URL, so that's the 3rd line, and then there's a 4th line. What we also did was make sure that any logging files or short summaries we uploaded as tokens. That made debugging, or at least keeping an eye on the processing, much easier. Because then you have a little bit more of a real-time feel for what's going on in your jobs. Overall, what I did, once it all worked out in the end, was, like I said, we were looking at 1 million, even a bit more of core hours, so this is not something you run in a couple of days, this is a month, 2 months, 3 months worth of effort. So basically once a week I just checked the token server output, and also on the command line I checked some of the status of the batch submission, etc. And that worked really well. I was very excited, because we found the first ever 2 new pulsars with LOFAR. This is a big deal for any new telescope. It shows that it works, and it means you can actually scale up, and in that sense I think these are the vanguard of tens or even hundreds of more to come. And just these 2 were already a great PhD thesis and a referee paper that we just got accepted. So I'm very happy about that. So for us this was a very successful pilot, and I hope that for you a similar experience happens soon. Thanks.